Let's take it from our realm of constant acceleration. I know the conservative work is equal to the negative change in potential energy. This is the integral of f dot dx. It's negative change in u. I'm going farther out, so my dx, or dr in this case, so dr is going to the right. What is the direction of the force of this object? Or the force, the conservative force on this object as it moves farther from the planet? Think of this as a satellite that got launched. Force diagram. Always drop back to that. What are all the forces acting on this object? Back towards the planet. Whichever way you consider positive, these are in opposite directions. So this is negative force due to gravity there. G mass 1 mass 2 over r squared dr. So negative G mass 1 mass 2 integral of r to the negative 2 dr from some initial value to some final value. Equals u initial minus u final. Same reasoning as before. So what's the integral of r to the negative 2 dr?
1 over r.
Close?
Negative.
Yeah.
Mhm.
So this becomes G mass 1 mass 2, I guess negative there, negative 1 over r from some initial to some final. The minus signs cancel out. So I'm left with G mass 1 mass 2 over r final minus G mass 1 mass 2 over r initial equals u initial minus u final. Therefore, what is a formula for u that will work?
G, big G, M1, M2 over R.
Close.
Close.
Didn't understand the question.
Plus a constant.
Okay. Still close. Unless I missed something. If this works here, this would be u final minus u initial.
So it's negative.
Negative. Plus a constant. So if the conservative force is the generalized gravitational formula, the potential energy formula is negative G mass 1 mass 2 over R plus a constant. Now, typically, you set the potential energy equal to 0 when R is equal to infinity. That is typical, but you don't have to. A couple years ago, I had a test question where I implied in the data that I gave in the problem that the potential energy was in a different spot. It's not an infinite distance away. I think every student missed that. They just automatically fell into the, oh, R is equal to, U is equal to 0, and R is equal to infinity. But we are now in the position to actually derive the formula for the short field radius. In other words, how big does our sun need to be, or how small does our sun need to be in order to become a black hole? So we can now get into some black hole physics, classical style. None of this general relativity stuff. But it comes out with the same formula. And that is where we're going to have to leave it.